All right, good morning, everybody. Today I'm going to be doing @Coder M Solutions programming contest. I don't really know what it's like, but it's rated for the same range that @Coder beginner contests are. So I'm just gonna, I guess, jump in and see if I can solve set. That's the goal. At the end of this, for all the problems I solve, I'll go over the solutions, and then if I have ideas for other problems and I wasn't able to solve them, but I'm still confident the idea is right, I'll talk about those as well. Yeah, so that's going to be the goal. All right, M. Kun is a competitor in @Coder whose highest rating is X. In this site, a competitor is given a class according to his or her rating. For ratings 40, 400 through up to this, the following cues are given. Okay, is there a pattern here so we don't have to type it? So it looks like it's like 8 minus the thing. Yeah, so starting at 400, every 200 subtracts 1. So that should be pretty easy to code. So a single test case, which is nice. And then x minus equals 400, because it starts at 400. And now let's just out 8 minus x over 200. Seems to be good. So if you are 1600 rating, and that's a rating of 2. If you're 725, that's a rating of 7. Is that right? Looks right. This needs to be main before we submit, and then we should be good to go. All right, so we got it. On to problem B, Magic 2. M-Kun has the following 3 cards: a red card with A, green card with B, blue card with C. He is a genius magician who can do the following operations at most k times. Choose one of the 3 cards and multiply it by 2. His magic is successful if both the following conditions are satisfied after the operations. At most k times, okay. The integer on the green card is strictly greater than the integer on the red card. The integer on the blue card is strictly greater than the integer on the green card. So you just do greedy. You multiply the green card by 2 until you're big enough. Then you multiply the blue card by 2. And very quickly you should have an answer. Everything starts small, so we shouldn't need to worry about overflow. Assuming there's only a single test case again, this should be quite easy. So while a at 1 is less than or equal to a at 0, a at 1 left shift equals 1, so times equals 2, k minus minus. Do the same thing a second time. Switch out k is greater than or equal to 0, then we can do it. So we print yes. Otherwise, we can't do it, so we print no. Very good. All right. Seems like we're good to go. Let's submit. Nice. Problem C, marks. Yeah, this has a much steeper, or not steeper difficulty curve, but like much wider, I guess. Like in Code Forces rounds, all the problems are much closer in their difficulty compared to @Coder. M. Kun is a student at this high school where a year is divided into n terms. There's an exam at the end of each term. According to those scores, students given a grade first through k minus 1th, not given. For kth through nth term, the multiplication of these scores in the last k exams, including the exam, the grading term. Scored this many at the exam at the end of the ith term. For each I, such that whatever, determine whether his grade for the ith term is strictly greater than the grade for the I minus 1th term. For each of the last k exams. Oh, so just determine if the products are increasing. So you have this product, then you have this product, etc. Got it. So basically, you want to compare the 100 and the 96, right? You'll divide out 96, but multiply in 100. And you want to see if that increases. Then you divide out 98 and multiply in 20. So the answer would be no. So you have to do this for each k. Oh, just for each position. Got it. That should be pretty easy to do then, I think. So let's do it. N equals this, k equals the next thing, and then we have an array. Good, and then what? Then we walk through the array. So we're comparing A at I is greater than, wait, strictly greater than? Yeah. So if this is greater than, or if this is greater than, well, if it's less than or equal to A at I plus k minus 1, then the answer is no. Otherwise, the answer is yes. Yes, no. Oh, I got that one wrong. How? Wait, how do I get this wrong? 1, 2, 3, 4, 5, 6, 7. 3, 1, 4, 1, 5, 9. That's 6. That's 7. So initially we drop the, yeah, we replace a 3 for a 6. So that is strictly greater. Now we replace a 1 for a 5. That's also strictly greater. Three for 2. Wait, is this? If we replace a 3 with a 2, that should be no. So if this is greater than or equal to, that should be like that. But that means I'm misunderstanding the problem. Yeah, this shouldn't be plus 1. It should just be like that. The very good sample, because other than the samples were like very easy, I passed them with a solution that was wrong on like 2 accounts. So let's go check all of these things again. Thank you for the sample. Appreciate it. Alright, so we've got A, B, and C. I think that's all been pretty good. We're on track, not spending too much time. We've spent like 10 minutes here. Road to millionaire. To become a millionaire, this person has decided to make money by trading in the next K days. Currently, he has 1,000 yen and no stocks. Only one kind of stock is issued in the country where he lives. Famous across the country for his ability to foresee the future, he already knows the price of the stock for the next N days and will be as follows. 1 for the first... Oh, wait. This many. Okay, so you're given an array of the prices, basically. On the 8th day, he can make the following trade any number of times. Excuse me. Any number of times within the amount of money of stocks he has at the time. He can pay this many yen and receive 1 stock, or he can sell 1 stock for this many yen. What's the maximum possible amount of money he can have at the end by trading optimally? So every time there's a decrease, you would want to make as much money as possible. And, or every time there's an increase, you want to make as much money as possible. And then every time there's a decrease, you would want to buy all of that. N's also very small, but that's fine. So, yeah, okay, so here we have an increase. And then here we also have an increase. So we find all maximal continuous increasing subsequences and then trade along those. And then to trade, you just buy as many as you can in the beginning and sell as many as you can in the end. So let's type that up. Int n equals this, and then array. Okay, so now what we want to do is we want to find all of the increasing subsequences of maximal length. For start 0, start is less than n, start plus int n equals start plus 1, while end is less than n, and a at end is greater than a at start. After this, we want to say, well, this will just be end plus plus. And now start equals end minus 1, and then it'll get incremented. So we increment it a bunch until we have a decrease. Then when we have this decrease, we want to sell as much as possible. So long money. How big can this get? Do they put a guarantee on the minimal? So it could double at most 40 times, right? So this needs to be a long. All right. So we have this subsequence. So now what do? We want to buy as many as possible to start. So long times equals money divided by a at start. And now money mod equals a at start. And now money, or money plus equals a at end minus 1 times the number of stocks we can buy. Stonks. And I think that's it. Then we skip to the end and continue going on the next day. Not right. Okay. Well, good to know. Greater than or equal to? Oh wait, we could buy... No, that would always be fine. Well, we might as well just do it every pair, right? So this is like just way too much work. Yep, okay, thank you. Get rid of that, get rid of this. And if start plus 1. So if a at end is greater than a at start, or is less than or equal to, then we can just continue. Otherwise, we can just do the sale for this day, right? That's fine. So money divided by equals a at start. Mod equals a at start. And 10 times. Yeah, okay. I don't know why the first one was wrong, but seems fine. Cool. So the runtime here is order n, and the max value is order 2 to the n over 2. So that's why the bound on n is so small. Good. Problem E, M's solution. At the center of the city, there stands a clock tower. Let 0, 0 be the coordinates of this point. A straight street, which we will call East-West Main Street, runs east-west and passes through the main street. Corresponds to the x-axis. There are infinitely many other streets along the y-coordinates. A straight street, which we can call North-South Main Street, is the y-axis. There are also infinitely many points parallel to the north-south Main Street, which are the x-coordinates. There are also n residential areas in New Atcoder City. The ith area is located within the intersection of... is located at the intersection. Residential areas are located at the intersection of roads. Okay. It's fine. You can just like define Manhattan distance however you'd like, but that's fine. All right. It has 2 railroads infinitely stretching, one along east-west and one along north-south. This mayor thinks they're not enough for the commuters, so he decides to choose K streets and build a railroad stretching infinitely along those streets. Let the walking distance of each citizen be the distance from his or her residential area to the nearest railroad. He wants to build a railroad so that the sum of walking distances of all citizens S is minimized. For each K, from 0, 1, 2, all the way to n, what is the maximum possible value of S? Maximum possible value of the sum of walking distances after building the railroads. Where are the citizens we care about? Surely we don't care about every citizen, right? Oh, n is the number of people? This text is too small, I can't read all of it. Oh, I see, the ith residential area. The sum of walking distance to all citizens is minimized. I see. So, like, you have different residential areas, but they have different priorities. Which maybe makes it more difficult. We can make one simplification maybe, which is if we knew we were only building horizontal streets, Wait, they already have streets at 0. It's kind of weird. Okay. Yeah, okay, so your distance changes depending on where you walk. So it seems like if we brute force which people walk to a horizontal road, that's a 2 to the n thing, right? So, well, first we're going to do a for loop up to n. Then we brute force which people walk horizontally. Now we know, like, we have this subset of people. We know how they're going to walk horizontally. How much time do I have? 3 seconds. Okay, not the end of the world. So we're going to brute force, yeah, which people go horizontally. Then we're also going to brute force how many railroads we have. And then we're going to brute force, or we can figure out where to place the railroads with a dp. That is n squared. So what is this runtime like? Wait, is this the last problem in the set? No, it's not. So n to brute force the number, well, to brute force like number of railroads, yeah. Then 2 to the n to brute force who walks horizontally. Now we need to do like n squared for the n times k, like knapsack dp within this to see how to distribute them. Maybe we could just do a 3 to the n though, that might be easier. Can I do 3 to the 15? I think so. 3 to the 15. I can. Good. So that's just this we can do with 3 to the n. 3 to the n pre-comp. For cost of each mask to person pair. Okay, so if we know who walks horizontally, excuse me, if we know who walks horizontally, we can figure out the cost of handling these people for as little as possible. Is it actually 3 to the n? Well, 3 to the n is cutting it close, right? This is 10 million, but it's not really 3 to the n. It's like 3 to the n times 15 at least. Yeah, it's 3 to the n times n. Well, it's low overhead at least. We'll try it. And then once we know that, then we can just add two totals up. So that should be very easy. Is there an easier way of handling this 3 to the n part? Because this is like, I think, the slow part. We could instead we have like a couple people otherwise. We could instead like if we're doing this dp, the dp is n cubed naively, right? So it's position last vertical and then lines left is the dp. So I don't know that n cubed is really any faster than, so like what's our final runtime? It's n times n cubed times 2 to the n times 2. So that's 15 to the 4th times 2 to the 16. Not gonna happen. All right, try again. So instead, we can do 15 times 2 to the 15. Well, times 3 to the 15, yeah, okay. So 15 times 15 times 15 times 3 to the 15. It's also not going to happen. But we can do the 3 to the 15 ahead of time. Yeah, so it's just 3 to the 15 times 2 times 15. Okay, I think that's actually fine though. So this needs to be pre-comped. And then we don't need this n cubed. We just brute force we brute force the number of railroads, we brute force who walks horizontally, then we brute force the number of points to give horizontally. Okay, so then what is that? So that's 15 times 15 times 2 to the 15. I think that's fine. So this is times 2 though. So this is the scary part. This pre-comp is very scary. But maybe I just do it anyway. Because maybe the operations are just so simple that I won't really get dinged for it. It's worth a shot. Okay. Let's write some efficient code. There might also just be a 2 to the n way of doing this that doesn't require all of these crazy optimizations, but I think that's fine. So int array x, y's, and then populations. Weights, I guess. So this equals next int. This equals next int. Weights die. Next int. All right, so we input all of this stuff. Now we need to do our pre-comp. Hang on a minute. Oh, that's fine. Okay. So int array. This is like if we place lines horizontally, this many cost. All right, so it's going to be if we place n lines and we want to cover the mask, this thing. So place n lines. Well, okay. Line h cost at I mask equals min cost to cover the mask, placing I lines. Yeah, okay. So we need the same thing with vertical lines, but we'll do that in a minute. So now we want to brute force what the outer mask is. So for int mask equals 0, well equals 0, mask is less than 2 to the n, mask plus plus. Now we also want to brute force the inner mask. So for inner equals mask, inner is greater than or equal to 0. Inner equals inner minus 1 and the mask. And if inner equals 0, break. All right, so now we need to figure out how do we do this part. So this is, we have some mask. We also know we have some places that we're going to place lines. We need to find the minimum cost of everything. Yeah, okay. So we want to do this in like order n time at worst. So int placed equals integer dot bit count of inner. Maybe plus 1, I guess. Like plus the 0, 1, but that's fine. Array placed in this new int array placed plus 1, maybe. Oh man, can these be negative? Why did they do this to us? This is very annoying. Okay, well, I don't want to sort it. If I sort it, I'll TLE. I guess we could make a free person that we always have. Yeah. So let's make a person class. Or set a class like town. Int x, y, weight, boolean free. Let's make it n plus 1, I guess. so maybe Boolean used. This is very scary. This runtime is very scary. What are the standings looking like? Do other people have this instantly or not? Holy cow. Oh, wait. Okay, good. So it's like everyone has these problems and then no one has these. So the difficulty is about what I would expect. And even XYZ, like I love chickpea and XYZ don't even have it. And this XYZ is an LGM. He's an MIT LGM, I think. Maybe it's a different XYZ. Yeah, but I think this is like Andrew He and Kason's teammate. And then I Love Chickpea is an old Polish LGM, I think, right? So if he doesn't have it, then we're in trouble. So I think the idea is we want to if we have these sorted by X, that would be nice. Sorted by Y equals new town array, n plus 1, and I equals 0, and then plus sorted by Y at I equals towns at I. Town, free town equals free town, 0, 0, cost of 0. So now sorted by Y, n equals free town. Raise that sort, sorted by Y, AB, turn, dot compare a dot y, b dot y. So now we'll have them sorted both by X and by Y. Which is helpful, I think. And now we can look at this. Yeah. All right. So now we can make an array of which ones we've placed. Yeah. For int I equals 0, I is less than n, I plus plus, mask at I, or if, well, temp mask equals, inner, while temp mask is not equal to 0. This is kind of like slow. Let's just do this. For int I equals 0, I is less than inner, or I is less than n, plus plus, towns at I dot used equals inner, and one left shift I not equal to 0. So that's whether we've used it. So now we know which towns we've used. Of course, we've always used the free one, but that's fine. Might not be important, but it's kind of helpful to have, I guess. Alright, so we've calculated all of these. So now, might also be helpful for these to have a cost, right? Yeah. For range I equals 0, I is less than or equal to n plus plus. Or we only care about some towns here. We only care about the towns in the mask. Yeah, okay, so well, let's just do a loop to I. I equals 0, I is less than n, I plus plus. Int last placed equals negative infinity. So I guess we could make this 0 and everything would be fine. Yeah, alright, so now sweep bottom to top. So if mask and 1 left shift I is equal to 0, then continue. Otherwise, we want to set last placed equals sorted by y at I. Ooh, darn. It's not how this works. Yeah, okay, so let's try this again. So we have this, these are like these used towns. Int n used equals to integer dot big count of the mask. So this is going to be n used plus 1. Or I guess, yeah, n used plus 1. Or just n used. And then we don't need this free one at all. We don't need these either. Okay, try again. So, we have all of these used towns. And use 0. If mask and 1 left shift I is not equal to 0, then used towns at n used plus plus equals towns at I. So this will fill out our list of used towns. Now, okay, well this is like the submask, right? So 4 and sub equals 0. Sub is less than 2 to the n used. Sub plus plus. So now we're looking at the sub-used masks, and we have to figure out the cost of these. We should probably also sort these by y. Compare a.y to b.y. Because the order of these ones doesn't actually matter. I guess we can call this inner, it's fine. So this is how many we placed. These positions don't matter. Yeah, okay. So, well, let's just say it just has one cost. That's it. So initially we need to set all costs to the distance from 0. Used towns I dot cost equals math dot min. Used towns I dot cost math dot abs. Used towns at I dot y. So that's the initial costs, but then we need to do a left to right sweep. So for, well, int last y equals 0, or int y equals 0, as is 9 x plus, last y equals, or if inner and 1 left shift I, this is not equal to 0, then last y equals used towns at I dot y. Okay. Then use towns at I dot cost equals math dot min. Used towns at I dot cost and use towns at I dot y minus last y. Now we just need to do the same thing. Well, this is initially the 0 dot min value. Now we just need to do the same thing backwards. So if we use this bit in the inner mask, then do this, otherwise do this. Okay, so now we have the cost for everything set. So now we need to do the total cost. How big can that be? Can cost 10 to the 6th for each of these, and then each of these can be 10 to the 4. Oh, really? You gotta be like that? Can be 10 to the 4 times 10 to the 6th. Why could they not just make it 10 to the 5th? What is the virtue of 10 to... All right, fine. We'll use longs. So here's the total. So now for... Are we still all right? Looks like it. All right, for town T and used towns, Total plus equals t dot cost times t dot weight. All right, so now these need to be longs. And then I think we're good. So then lines h cost at placed. Placed mask equals total. So we've done this pre-comp. We know the min cost of placing each mask, so we can help each mask of people if we place this many lines. Good. So for int lines to place equals 0, lines to place less than or equal to, what do we print? We print it after from 0 to n. Okay, less than or equal to n lines to place plus plus. So now we're placing this many lines. Good. For int h, oh, we have to do this whole thing a second time. Okay, copy and paste. Lines v cost equals new mask this. Mask goes from 1 to n. The number of used, well, syntax highlighting please. Number of used equals the bit count of the mask. Here are the used towns. Okay, sort these by x this time. There's your inner for loop. Last y is the min value. This should be last x though. So now we go from 0 to n. We want to update last x with useTowns.x. And then useTowns.x minus last x is the idea. Now last x equals the max value. And we go backwards like that. Last x. Okay, so the line total equals this, total times equals this. Okay, so I think that's fine. So now we have vertical cost and also the horizontal cost. Oh wait, lines v cost here. All right, good. So now here are the lines to place. So now we need to worry about our masks. So for int hmask equals 0, hmask is less than 2 to the n, hmask plus plus. So now we need to brute force how many lines go horizontal. For int h lines equals 0, h lines less than lines to place, h lines plus plus. Int v lines equals lines to place minus h lines. Okay. So now we need the minimum cost. Right, that's the best. So int min cost equals integer or equals, it's a long min cost equals long max value. Sys out min cost. So we know how many lines we're going to place. We also know the mask of the people we're going to help horizontally. So int full mask is going to be 1 to the n, or 2 to the n, minus 1. So that's everything. And then int v mask would be full mask, but not the h mask. All right. So now long per cost will be the lines v cost at the v, or at v lines. We place this many lines, the v mask will be v mask, and then plus lines h cost at h lines with the h mask. Cool. And now min cost equals math.min, min cost per cost. So that's a lot of bit magic going on. Seems fairly likely I messed something up, but there's a chance it's right. These shouldn't be N, these should be placed. Placed -1. Alright, these should also be placed. And this should be N. This should also be N. Should also be N. Oh, lines to place less than this. Yeah, yes, and each line's less than less than lines to place, also less than the bit mask of H, I think, right? Or maybe that doesn't matter too much. That'll just be 0 anyway, I think. So that should be fine. Not even close. Oh, I see. The lines to place needs to be up to n+1. But why did this not crash then? Okay, that's a problem. This is also a problem. Okay, something is terribly wrong. This shouldn't be integer to, oh, that can be integer to max, that's fine. Well, let's look at this then, maybe. See what's going on. Oh, these are .y, these are .x. This should be .y. Yeah, okay. Oh, these are negative. These shouldn't be negative. This should be last x minus this. And this should be minus that. That's something. Alright, still very wrong. So now let's consider the cost of helping each person. So, yeah. Alright, so placing mask. This mask to binary string mask with inner plus inner gives plus total. Placing 0, yeah, okay, with 0 gives 0, good. Placing 1 with 0 should not give 0. This should be 0, this should not be 0. For each town, it costs 0. Why would that be the case? Let's use town or plus t dot y. So y is 2. How big can the coordinates get? Alright, so this needs to be int 1e8. Negative int 1e8. This needs to be just regular 1e8. And then these ones as well. Or this one's negative, right? Yeah. So that would explain the negative answers because they're overflowing. This is not right, but that's fine. Placing mask 1 with inner gives 0. So why is it that this is returning 0? Because it shouldn't be. Cost of this thing should definitely not be 0. Initially, its cost will be 2, because its y is 2. So now we go through every placed item. Not placed. Should be unused. Oh man. Every used item. That many placed, that's fine. So that's placed. We want to go through each used item. Okay. That would explain a lot. This easy, nice sample in the beginning is very helpful. Okay, placed mask 0 with inner 0 gives 0. That's fine. Placed mask 1 with inner 0 gives 0. That's not fine. So the mask is 1, the inner is 0. Cost at 0 is 0. Should not be 0. Equals just this. Well, we got one of them right, didn't we? No. But now we're getting real numbers as answers. Placing one mask with the inner of 0 gives 600. So if we walk horizontally there, it costs 600. Yeah, I suppose that's right. 2 times 300, right? Yeah, that's fine. What answer are we looking for? 2,900? So that means it's 300 plus 1,800 plus 800. So 3 plus 18 plus 8 is 29, yeah. Okay. This is 600. One mask with an inner of 1 gives 0. We take just this guy with an inner of 0, gives 1800. This mask with an inner of 1 gives 0. Taking the first two with nothing gives 2400, so 18 plus 600. So 18 plus 6 is 24, yeah, that sounds right. Maybe we check like the big thing. So inner of 2 this is interesting. So the inner is 2. That means we place a y, or we place one at this y, just a y3. Why is the cost of this 0? Initially it's 2, 3, 4. How does this get to 0? Putting an infinity number, 2, that's odd. So placing everything at inner 2. So initially it's 2, 1, 0. Now we visit this first thing. We said its cost is 0. Why would we do that? So it's initially its cost was 2. This should be 0. Oh, was I reading the wrong thing? Yeah, maybe I was reading the wrong thing. Oops. So 2, 0, 1, 1, 0, 1. Yeah, that's fine. Okay, I'm just stupid. I think that should be fine. Alright, so let's try this. So now we calculate these. That might be fine, sys out. Alright, so now sys out. What the heck? Oh, less than or equal to lines to place. And that's it. Okay. Cool. Lots of debugging, but I think that should be reasonable to some degree. Yeah. Unresolved compilation. Good, okay. How's this? These pictures are nice. I do appreciate them. We got it wrong. No. Alright, do we get these other ones right? Or am I just being like overly confident and not actually reading all the output? 2900, 900, 00. Okay. 8 or 13, 800. Okay, not right. Is this other one simpler? Probably not. Let's look at this one then. 13,800, 1,600. Am I not finding a good enough answer? Yeah, okay. So I get 0 lines right. I just get 1 line wrong. So it should be 400 times 2, right? Be 1600 is the answer? Yeah. Now I don't print 1600. Let's try this really quickly, I guess. We'll just redo this part in case there are any mistakes in it. So sort by x. Cost is the absolute value of our x. Cost here is the absolute value of the x. X minus last x. This should be last x. Last x equals a big number. Last x equals this thing's x. Last x equals this thing's x. Total equals 0. Cost times the weight. Set lines v cost to this thing. Okay, so are we still wrong? We probably should be. Okay. So now we're interested in the case in which lines v cost equals, yeah. So if, well, let's do a print statement. So Boolean print equals inner equals 1 left shift 5, or 1 inner equals, well, what would it be? I guess 2. And mask equals 1 left shift n minus 1. So if print source total. Town costs are 3, 5, and 2. Yeah, that's fine. 7, 5, and 2. The total is 1600. What? What is going on? I'm very confused. How do I get this wrong? So am I just adding like some vertical cost even though there shouldn't be any? So for the horizontal cost of 0, the number of horizontal lines of 0, I'm paying $6,000. What? Plus integer to binary string vmask plus vlines plus zero zero all ones gives me $6,000. Total placed. How many lines am I placing? And the mask should be everything. Int equals. Oh, I see. Ah, okay, that's silly. Yeah. Okay, that's really stupid. How much time do I have left? 15 minutes? Yeah, I can fix this. So the issue is this thing right here. Okay, so lines d cost at I j equals integer dot max value or 0. So it's integer dot max value if I is less than or equal to integer dot bit count of j. Well, less than. Otherwise, it's definitely 0. Same thing with the horizontal stuff. Equals math.min lines h cost at placed mask total. There we go. Thank you. Okay. Try number 2. That stuff looks good. That actually looks good this time. Uh, 26700, 13900, 3200, 1200, and a bunch of hundreds. Yeah, from a quick scan that looks fine. The last digits are fine. So it seems like it's all right. Okay. Let's submit. I'm going to have to optimize for a TLE. Darn it. Ugh. So generate a TLE case then, right? That's the idea. So 15 things. 1, 1, 1, or 2, 2, 3, 3, 3. It's so close too. It's so close. So is it the pre-comp or the rest of it that's killing me? It's the pre-comp, it looks like. Oh, it's kind of both of it, to be honest. Current time. Four seconds. It's 4.2 seconds. Oh, it's killing me, man. It's killing me. Okay, how do I fix it? What's going to be the slow part in here? Sorting doesn't happen that much. This doesn't happen that much. It's this inner loop that's dangerous. Maybe we can pre-comp this. Well, bit count can't be that slow. Oh, the mins and the maxes. Let's do our own min method or our own max method. Static int min int a b, return a is less than b, a b. This isn't actually crazy because for whatever reason this is like super slow for Java machines, calling mat.min or whatever. Not much faster though. Well, we iterate through everything here. Yeah, we kind of have to do that here. So we could maybe just try and speed this up. Oh wait, this isn't actually the entire pre-comp. This is only half the pre-comp. Okay, it's just all the pre-comp. The pre-comp is the entire part. This 3 to the n thing. So this part is 3 to the n, that's fine. Do I have enough time to convert to C++? Probably not. So a lot of stuff. If you comment this out, it doesn't go much faster, right? Yeah, this part's not going to affect it at all. So that's fine. We don't need to worry about that. It's this inner loop that's really slow. So how do I fix this? I could make the bit count better, maybe. But this is the slow part. It's min. 3.8 seconds. It's still not as nice as I would like. So maybe pre-count my bit counts. Alright, so now we need this to be bit count and mask. Bit count at inner. Bit count of I. What is wrong here? What have I done? This should be fine at least, though. Oh, this should be one left shift n, that's the problem. Oh man, okay, fine. Integer dot bit count at. All right. How much time do I have left? 2 minutes. Come on. That was not faster at all. Arr. This is 3 to the n. The absolute value call. Well, we can get rid of it. So this just needs to be AX. This needs to be AY. Whoa, so much faster. Okay, we're submitting that for sure. Oh no. Oh, I shouldn't have changed it to main. Still probably not fast enough though. If I have the right runtime and I'm just getting Java, I'm gonna be very upset. Tilly. What is the runtime? What are they looking for? Is it not a 3 to the n? Why would it be 15 if that were the case? Oh, yeah, wrong answer too. So something I changed was wrong. Oh wait, it was wrong earlier. Ah. Well, unfortunate. We did pretty terrible. Pretty terrible. Oh, and E, it looks like E was easier even, and I didn't even read it, or F was easier. Oh well. Yeah. I guess I just kind of spent the entire contest on problem E. So maybe that wasn't a good strategy in hindsight. Kind of hard to tell. Let's go over solutions, I guess. So, yeah. So for problem A, you have a bunch of ranges, and you have to figure out which range you are part of. So that looks kind of like this. The ranges in particular, oh, hang on. The ranges look like, they're like 400 to 400 plus 199. So roughly 400 to like, what is that, 599? And then you've got 600 to 799. Oh, that handwriting is absolutely horrific. 799. Yeah, and then like 800 to whatever. So what you can do, and this corresponds to rating 8. And this is like rating 7, this is rating 6. So one thing you could do is just hard code all of them. There are only 8 possibilities, so it wouldn't take that long. If you want to code it faster, you can start at 400 and then like floor the number of things over 200, right? So if it's like X, if X is your rating, then X minus 400 is the amount that's like actually relevant. This divided by 200 floored, that's how many times you subtract your rating, and then it's 8 minus this. So that's the simple one-line formula. And that's problem A. Problem B was almost as easy. And you have 3 cards in problem B. So you've got like some A card, some B card, and some C card. And then you want A to be less than B and B to be less than C. The only operation you can do is like some number times equals 2. So you want A to be as small as possible because there's no reason not to have it like that. So you keep A what it is. You multiply B by 2 until it's big enough, and then you multiply C by 2 until it's big enough. And you'll never have issues with overflow because all of the card sizes start tiny. They're all like 7 or less or something. So yeah, you can just multiply B by 2 until it's big enough, multiply C by 2 until it's big enough. That's how many moves you need. And then you just check if you have at least that many moves. That's problem B. Awesome. Problem C. Oh yeah, problem C is kind of interesting. So in problem C, you've got like some array. So maybe the array looks like, let's use one of these input arrays. So 96, 98, 95, 120. Then you have a range of like 3. So you want to see what happens to your exam scores, whether it increases or decreases in consecutive terms. Now, the important part is the only difference between these terms is like the first element and the last element. This element gets added, or gets subtracted rather, and this element gets added. The rest of the elements are all the same. So all you need to do to compare like their relative products is to look at whether the number you add is bigger or smaller than the one you subtract. Or when I say add, like add to the range, you're multiplying it in, but yeah. So since everything's positive, it's just bigger or smaller. But anyway, you just want to see whether it's an increase or a decrease. And if it is an increase, that means your product gets bigger. Otherwise, your product gets smaller. Cool. Yeah, so then you just do that. If this is like length k, then you check like index I to index I plus k. And that'll determine whether it gets better or worse. And you just have to handle like the equals case in a smart way. Like if it stays the same, then you have to print no, I think. All right, very good. Let's look at problem D now. So to become a millionaire, you've decided to trade the next k days. Yeah, so it feels like all of these problems are just like incredibly easy, and then I hit problem E and just couldn't do it. But oh well. So yeah, for problem D, the idea is like you have stocks at a bunch of days, so maybe, or stocks at a bunch of prices over several days. Maybe it's like this, and then like this here. Maybe here are your prices over time. So like the vertical axis here is price, and then this axis is time. So what you want to do is you want to like make as much money as you can. The idea behind doing that is you want to like buy low and then sell high, and then your profit will be this amount here. That's how much you'll profit times the number of stocks you bought. So you want to do this as many times as possible. You want to maximize the length of this profit, but you can do it multiple times, right? So initially what I was trying to do is like just like find these maximal jumps, but you don't need to actually worry about that. You can just do this here, and then after you do this, you can do this, and that works just as well. You can just like consider them separately, which means you only need to consider adjacent ranges ever. It's fine to buy one day and sell the next, and that's all you ever need to do, because you can just buy that next day as well, and that'll like just like be the same as not selling. So anytime you have an adjacent increase, that means you want to buy in the first day and sell on the second day. And since you know it's going to be a profit, you want to buy as much as you possibly can and then sell all of it on that second day. And then you might rebuy all of it the second day as well. But yeah, that's the goal. So that's the idea. Just check all adjacent pairs. If it's an increase, then buy as much as you can the first day, sell all of it the next day. Your profit is just this distance here times the number of stocks you can afford on the first day. And then you just sell your last day, and then you're good to go. So that's problem D. Problem F, I didn't actually read, but problem E, I think I know how to do, or at least I have an idea for a solution. Here's the editorial. What's the, it's not in English. Do we have an English version somewhere? Okay, does it have the runtime? Maybe it has the runtime and I can read the runtime. 2 to the n times n squared dp 3 to the n times n. That's my I'm being Java'd. Or maybe this is like a suboptimal solution. You can get it to be better. No, this is sum over subset. Or this is yeah, this is 3 to the n. Maybe they don't have a times n in it. They do have a times n in it. Well, I feel cheated. I feel like I have the right solution now, and they just didn't let me get it to pass. That's very unfortunate. Maybe I'll just convert my stuff to C++, and then it'll pass in C++. Anyway, all right, so the idea behind problem E is you have like two railroads already built, which are the XY axis. And then you have a bunch of points on the plane. So maybe you've got like this point here, 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 here. This was a good case, I think. And what you want to do is consider building some more railroads. Each railroad is either horizontal or vertical. And you want to do it so that the total distance from every node to a railroad is minimal, but also the nodes have different weights. So each node is like its distance multiplied by its weight because it has like different populations or something. So in this case, for like if everything's weighted equally, the first time we might want to draw this road here. And then the next time, if we draw this road here, then we've covered everyone in just two roads. But you can move the roads between turns. So like if initially, like if instead of the thing above, you have something like this, then, or maybe it's like this. So then maybe the first turn the optimal, and then like let's get rid of these ones on the top. So it's possible the first turn the optimal road is like this, and then the next turn it's like this. That's the idea. So that you can, they're not fixed when you place them one by one. So now for each number of roads you might want to place, you want to say what's the minimum cost of doing that. So the solution idea is, let's imagine it in the one-dimensional case first. So if everything's just on a line, and you have a bunch of points, what you can always do is you can always move the line, like let's say this is your vertical line. You can always take this line and move it over until you're at one of the points. So that's the observation. The reason for that is if you have more points on here, this is bigger, then let's say this is like 5 and this is 4. Then if you move it a little distance over here, you've decreased your total by this times 5 and only increased it by this times 4, which means it's beneficial to move it to the right. And you want to keep doing that until you're on this 5th point. And after that, moving it to the right will increase it by 5, moving it to the left will also increase it by 5. So both ways, like moving it in either direction from this point would be bad. That's if there are an odd number of points. If it's even, if you have 5 and 5, and then you're not in the middle, then it's fine to move it over to the right. It doesn't hurt you. And it's fine to do that up until you're at some point. So some optimal answer always has the line going through a point. That's also true in 2 dimensions. So all of the horizontal and vertical lines you'd want to draw are lines that actually just like cross some of the points. And if we like are looking at this 2D case, we can pretty easily simplify it to the 1D case as well. So say we've got some points, maybe like this or whatever, and we also have some roads. Then basically what we're doing is we can brute force which points we know are going to like walk vertically. So once we say, let's imagine these 3 points walk vertically, then we have some vertical line. We'll solve this problem. Probably the best solution to this would be like this, maybe, I'd say. It's a very plausible solution. So now this would walk here, this would walk here. But now, since we know all of these points are walking to a vertical line, then we don't have to consider the rest of the points at all, and we also don't have to consider any of the horizontal lines. Really, we just have like a single vertical line, and then we have the point here, here, and here. And now the question is just how do we solve this in a 1D case? So yeah, and then once we have this, now we can also look at these other points here, and we can consider these in the vertical case. So we just have 2 smaller problems. So that's the idea behind the solution. We're going to brute force the which ones like walk horizontally and which ones walk vertically. Now, we also need to brute force like how many ways are there to distribute lines among these, and we can do this a little bit better. So here's the idea behind that. So yeah, so if we brute force like we've got a bunch of points here, we're going to brute force which points we choose to have to walk in some direction. First we'll do vertically, then we'll do horizontally. So let's just talk about, they're just going to walk in a horizontal direction to a vertical line. Right, so they're walking horizontally. So let's say we find some subset, we brute force what this subset is. Now we want to brute force what subset of these points have a line on them. So maybe it's like this point has a line. Once we have this, we know this point has a line on it. Now we can do a sweep from left to right to figure out what the cost is. But the hard part is we're brute forcing all subsets that have this line. So you might think that that's going to take 4 to the n in total, because we're doing 2 to the n to like brute force which points, like which points are in the set. After we do that, we do another 2 to the like number of points in set to figure out which have horizontal lines. Or yeah, which have lines, I guess. So here are the two things. Now this can be all the way up to n. So like worst case, you might think that this is n to the 4th, but it's not actually, and here's why. So for each point, we can make this like this little table. We can say, is this in set, and is it, or does it have a line? So initially, if we just do this naively, it could be in the set and it could also have a line. It could be in the set and not have a line. It could be in the set, or it could be not in the set and it could have a, or it could not have a line. It could also be in the set and not, or it could not be in the set but have a line. So if we are smart about this, what we can do is we can eliminate this case here, because these aren't important. We don't want to consider points that aren't in the set but have a line, because if they're not in the set, then there's no reason to consider a line going through them. So you can do this, like there's this cool trick you can do. So like your outer mask goes from like 0 to 2 to the n. But then you can say like your inner mask goes from the mask down to 0. But at each step, you want to say mask and equals with the, or the inner mask. So inner, I-N-N-I-E-R, cannot spell. Inner and equals the mask. So this will like remove all of the bits that aren't important, which will, I guess, make it faster. That way you only consider things that are in one of these 3 cases, and you don't consider something where it's in the set but doesn't have a line. So now since each point can be one of these 3 different possibilities, the total number of things that you see in this inner for loop is only like, it's one of these 3 things for each bit. So it's 3 to the n if you eliminate checking all of these 4th possibilities. And like, just to be clear, you're not iterating through them and then writing an if statement to say if this is true, whatever. You're just not even considering them in your for loop. Because you do this and statement, you're just like skipping over all of them in one step. So like none of these bottom ones even get considered. The total number of operations is just one of each of these states for each node. Okay. Yeah. So that's the idea behind the solution. Once you know the cost of doing like one group horizontally, you brute force the horizontal group, and then you also brute force how many lines to distribute to them. And that's the idea. From the numbers that I saw in the editorial, it looks like this is intended. But it's possible this is like an alternate solution, and there's a 2 to the n as well. In Java, it seems like it takes 3.5 seconds. And then also I have a small bug somewhere, so I think it's wrong maybe. Or my code is wrong. I'm pretty sure the solution idea is right. But yeah, I don't really know. So let's see if ratings are out yet, because this is kind of like the road to unrated, right? That's the goal. Oh, I went down. Yeah, no, that's understandable. Okay, fair enough. I didn't do very well anyway. But yeah, so hopefully, but I'm like in range now, so hopefully next weekend, whenever the next ABC level thing is, I should be able to get to 2,000. That's the goal, and then these will become unrated for me. So we'll see. Well, anyway, I hope you enjoyed the contest. Hopefully you did well, and I hope you liked the problems as much as I did. Thank you for watching, and goodbye.